I think that there are several, as I teach my class, there are several factors that support the majority of the additional CO2 being leaked to fossil fuels. And let me go through them, okay? One is the timing of the rise is more or less coincident with the onset of fossil fuel use. The second is that the magnitude of the rise is within a factor of 2 about right. There is what's called the airborne fraction, which I'm sure you know well, which is about a half. The third is that there is a difference between the northern and southern hemisphere. The northern hemisphere concentrations lead the southern hemisphere, which is where most of the emissions happen. The fourth is the isotopic ratio. The C13 is going down, as you said. But the fifth, which you didn't mention also, is that the oxygen in the air is going down a little bit, not enough to worry about being able to breathe at all. But it is a signature, says the scientific literature, that we're pulling reduced carbon out of the ground. Okay? So those 5 things for me are pretty persuasive. Now, you would ask, why didn't I inject any doubt at all? And in fact, I tried not to inject any doubt at all in the book. And frankly, that's a tactic. While I know that there are reasons to question the science itself in the IPCC, I knew if I started to do that, it would be dismissed, the book. Okay? Whereas it's much more powerful, I think, and I think it's turned out to be the case, to just quote the IPCC back to them. Okay? All right. As a second phase, once you open up the fact that the IPCC has not been telling the complete story, then you can get into discussions of the kind that you're talking about. All right? So the IPCC uses an ensemble of models, about 40 of them or so, that are produced by different groups around the world with different assumptions. And then they compile this ensemble all together to intercompare them and compare them with the data. And if you look at this chart on the right, it shows the sensitivity of 40 of the models. Namely, if we were to increase the CO2 by 2 times, how much would the temperature go up? And what you can see is that 40% of the models, the ones shown in yellow, were deemed too sensitive by the IPCC and thrown out of consideration in evaluating the climate sensitivity. It's in the book, actually, already, this discussion, because I knew the IPCC was going to have trouble. Right? And it's a little bit disconcerting to me that the world's best modelers, trying as hard as they could, are still getting it wrong 40% of the time. It's even worse when you look at their ability or inability to reproduce the historical global temperature. Here on the left panel is the global temperature in black over since 1880 up until the present. And the individual lines in the spaghetti diagram are the individual models. And you can see that a good number of them miss the historical data, the real data, by as much as the difference we're all arguing about. Nevertheless, they just average all of this stuff together, and that gives the answer. The problem here is thought to be an imbalance between the sensitivity to greenhouse gases and aerosols. Aerosols cool. If you're too sensitive to aerosols, you dip too far down. If you're too sensitive to greenhouse gases, you zoom up too far. The net is the balance between those two, so you can have a high greenhouse gas sensitivity and a high aerosol sensitivity, or a low sensitivity to both, and still more or less get the data. So what that letter was about that you referred to, was that even though they threw it out in assessing the sensitivity, the people who used the output from these models to worry about impacts on vegetation, on mortality, were still using the entire ensemble and not throwing out these yellow ones. And so that was a plea from Gavin Schmidt and some other people in the consensus saying, don't pay attention to the hot models as you try to analyze these impacts. And of course, that will mean that the impacts will be less as people churn through them. All right? The reason I didn't talk about sea level rise is I just don't have the time, but I do have the charts, and I'm going to pull them up for you in a second. There we go. All right. So this is the data that you mentioned. This shows the sea level rise over 20,000 years, as inferred from the geological record. And indeed, as the last glaciers disappeared 20,000 years ago, the water went from the land into the oceans, and sea level rose rapidly. And then about 8,000 years ago, it started to rise much more slowly. And so the question we're trying to answer today is, has the sea level rise accelerated under human influences as opposed to natural influences? That discussion hinges on 1/10 of a millimeter per year differences in the rate of rise. I'd like to know to what extent is that acceleration, if it's there, human caused, and of course what's going to happen in the next few centuries. Here is the results from a paper that the IPCC cites. I think it's actually a pretty good one, in which they've looked at the trend rate of rise in global mean sea level due to various causes. The observed rise is the blue, and you can see it goes up and down. Right? It was, again, as high in the 1940s as it was in 1990. It's a little bit higher now. And it's got various contributions to it. I don't want to go through it in detail. But let's talk about projections, okay, over the next 50 or 100 years. We measure sea level by two methods. One is the tide gauges that have been at various places around the world for more than a century in some places. And the other is through the satellites. The satellites measure the sea level height, and there's, I know, a big French effort both to deploy the satellites and analyze the data. And they don't agree with each other. The satellite people say it's accelerating, whereas if you look in the tide gauges, it's pretty hard to find an acceleration. What matters, of course, is what the sea level is in various places around the world at cities. And fortunately, there's been a tide gauge at the southern tip of Manhattan, which is called the Battery, since about 1860. And so we have official government numbers of the sea level over 160 years, which is called the Battery, since about 1860. And so we have official government numbers of the sea level over 160 years. There's a gap of about 20 years in the late 19th century. You can take that data and analyze it, and you get the black curve for the 30-year rate of rise. Right? So first of all, it averages about 3 millimeters a year, which is a foot a century. But surprisingly, it goes up and down also. And currently, at least when this graph was made a couple months ago, it was high, but the question is, what's it going to do in the future? When you read the official government report that the U.S. National Ocean and Atmospheres Administration issued in the beginning of 2022, about a year ago, they said it's guaranteed, locked in, independent of the model, independent of emissions, that this graph is going to go up to there. that we would see a rate of rise by 2050 equivalent to 10 millimeters a year, 3 times the average and 2.5 times the current rate. We will see, okay? But look at what some of the experts say. These are people from Columbia. The use of climate models to guide local practical adaptation action is unwarranted. Climate models can't represent future conditions with anything like the degree of spatial, temporal, or probabilistic precision with which projections are often provided. And they give a false impression of confidence to users of climate change information. You know, who am I to contradict the IPCC that says it's going to go up by a meter, but actually they cover themselves because they say it'll go up between 30 centimeters and 2 meters. So they can't be wrong. All right? When you look at this graph, we'll know within a decade whether the red thing is right or not. So, not to wait too long to find out. I don't believe him. As my friend Will Happer would say, he'll bet his house that that doesn't happen. I think the current passion, fervor for the energy transition is really, I'm not going to use the word conspiracy because I don't think it is that, but it is an alignment of interests. So let's go through the actors, right? The media first, okay? We have a saying in English, if it bleeds, it leads. And so news about impending threats is much more click-worthy than news that there's not much of a problem, all right? We're psychologically tuned to pay attention to threats. So the media like to promote alarm, or at least have an incentive to promote alarm. The governments, I think it's nicely captured by a quote from H.L. Mencken. He was a journalist writing in the US in the early 20th century. And he's got a quote in one of his books that says, "The purpose of practical politics is to keep the public alarmed by a series of mostly imaginary hobgoblins so as to be clamoring to be led to safety." And when you look at the political landscape with that lens, things start to make a lot of sense. Climate, in the US, immigration, COVID, et cetera, et cetera. So governments would prefer to have a threat than not. Now, let's look at the NGOs. If you've started an organization whose purpose is to save the earth by reducing carbon dioxide, and you're told this is not as much of a problem as you thought it was, you're not very happy and you won't publicize that. And then the scientists, I think most of the working level scientists I've talked with have the best standards and traditions that we all have. With all the caveats, all the uncertainty, I have not had a serious scientific criticism of what I've written in the book that at least I think has been valid. I have a good friend who's an eminent earth scientist, and I asked him, what do you think about the book? And he said, I think you got it exactly right, but there's one figure out of the 70 that I would take issue with. But there are some scientists, whether it's because of funding, prominence, it feels pretty good to be saving the earth, that have distorted the science. Right? And again, I've tried to get behind all of that and expose what's really going on. I've often said the best introduction I had in a long time was from Benny Peiser, who runs the Global Warming Policy Foundation in the UK. And Benny introduced me by saying I was like William Tyndall. And I'm not a historian, so I had to look him up. Discovered that he was the first person in the early 16th century to translate the Bible from Greek and Hebrew into English, and so exposed to the ordinary people who could read what the Bible really said as opposed to what the church said it said. And of course, he was burned at the stake for doing that. Okay, so that's my analysis of the players and motivations. I know John very well. We communicate often. He is a scientist of the highest integrity, and I think what was done to him was a scandal. The numbers are simple, okay? The U.S. today accounts for 13% of greenhouse gas emissions. If the U.S. were to go to zero tomorrow, the growth of the rest of the world, and particularly the developing world, would negate that decline in about a decade. Maybe it's 15 years, okay? And so you would not reduce the concentration at all by very much. As long as you keep emitting, the concentration keeps going up. And so zeroing emissions globally just means that we've stabilized human emissions, human influences, and it's going to take a couple centuries for them to start to decline. So reducing emissions by a little bit just delays the rise of the concentration. It does not prevent it. My guess is most people don't understand that. There are many things I've not been able to talk about, limited time and so on. In this deck, I don't have charts about geothermal, but I do in other decks. So if you want to have impact, it's about scale and cost. The cost has got to be competitive with other methods, with whatever subsidies you want to put in. You cannot subsidize to scale, okay? It just cannot. Governments don't have that money. They can subsidize demonstrations, initial deployment, and so on. With respect to geothermal itself, I see 2 or 3 issues. Cost of drilling, right, is pretty expensive. The cost of the casing, because you're dealing with very corrosive hot materials. We don't know how long they're going to last. And so there's an expense or a lifetime issue there. And then there's an unknown. If you drill an injection well and a production well, you pipe down the fluid during one and bring it up in the other, use the hot fluid to turn a turbine. You're drawing heat away from the surrounding rock. And the question is, if you draw it too fast, it's not going to be able to diffuse back to where you're extracting it from. So there's a question of, to use the oil field lingo, the decline in production. All right? And I think those are all unknown. Shallow geothermal works well. There's a plant in California, there's one in New Zealand. They run at 100 megawatts where you have the hot water near the surface. But if you have to go down deep, you run into the issues I mentioned. Plus, we don't know exactly where the heat is shallowly. We have no way of exploring for heat. Of course, it's down there at some depth, but you'd like it to be pretty shallow if you could get it. We don't. So I think it's one of a menu of technologies, but it's a question of cost and scale. Kind of a basic fact first about the climate system. The human influences on the climate system are physically small at the 1% level. The flow of power in and out of the system is just about 240 watts per square meter. The human influences are 2.4 watts per square meter. So 1% perturbation. Some real skeptics, not informed skeptics, ask, well, 1%, how can that make a difference? But doing a physics-style estimate, If there's a 1% perturbation in the energy flows, you would expect a 1% perturbation in the temperature. The temperature is not 15 degrees, but it's 300 degrees, because we need to measure in Kelvin, and 1% of 300 is about 3 degrees. Now, there are many other factors that go into connecting the influence to the temperature, but it shows, first of all, that it's not crazy that 1% can make a change in the temperature that we care about, but also that because the influence is small, there are many other factors that could be that size, and so we're down, if you like, in the weeds, trying to untangle human influences from other influences or natural variability. As far as direct solar influence, in terms of the sunlight that the sun produces, I think the IPCC has pretty convincingly ruled that out. We have instruments that can measure very precisely the amount of sunlight, including in the near-infrared, that comes from the sun, and the changes that we see are an order of magnitude too small to account for the temperature. But the sun may well have other influences, for example, through changes in its magnetic field, which can modulate the cosmic rays, through changes in its spectrum, and so on. People have looked real hard for that, to find signatures, to find mechanisms where that might happen. So far, I would say nothing really conclusive, but I would still hold the door open to some surprises because it's small effects in a noisy system for which we have very limited data on the timescales that are important. Okay? So I'm sorry, it's unsettled, all right, what you ask about. Again, for those of you who may not know the background, Lorenz at MIT was in the early 60s, 63 I think, was studying not a full-blown climate model, but a system of 3 nonlinear differential equations, and discovered this remarkable property of chaos, which has become a fundamental principle and object of understanding about many aspects of the world. I think that does not necessarily apply to the real climate system, and let me tell you why I would hold out some expectation that it doesn't. Lorenz only used 3 equations, and he found this chaos. Let's jump to a much more complicated system. Let's take the molecules in a gas, 10 to the 9th, or 10 to the 23rd. And if you wrote down the differential equations that describe their motion, there's a potential between them, nonlinear, chaos, you would quickly realize that the system was chaotic, guaranteed. Nevertheless, it's perfectly possible to model the bulk properties of that gas. Sound waves, shock waves, fluid flow, and so on. Those are, at some level, not chaotic systems at all, though fluid flow eventually is. And the reason that it's not chaotic, and we can describe the system with a pretty good computer, is because there's a separation of scales. There are a lot of molecules. They all interact on short times and short distances, and we're interested in properties that average over that. In the climate system, I think it's still up for grabs as to whether there is a separation of scales or not. It's kind of in the middle. And so do I believe that you could, in principle, if you got it all right, predict the average temperature rise as you increase the CO2? Probably. But there's a lot of chaos between here and there. So this is a chart that I use that shows some of the problems in the modeling, and maybe if I spent a minute going through that, that would be useful. First of all, it's a grand computational challenge. The way we model is to cut the atmosphere and the ocean into boxes, and then follow the flow of energy, matter, water vapor, momentum through those boxes step by step over 10 minutes. And you've got to do that over thousands of years in order to try to understand the climate. So it turns out you need about 10 to the 8th voxels over 10 to the 8th time steps, so 10 to the 16th numbers in the computer. And you've got to do that with a precision of 10 to the minus 3. As I told you, human influences are 10 to the minus 2, so you need a tenth of that. As I've shown you, we have many discrepant models that disagree with themselves and with the data. And you're going to ask, how could that be? It's just physics, you hear people say. One of the major ones is what's called subgrid parameterizations. So if you cut the Earth into boxes, you can only make the boxes so small, otherwise you get too many boxes to have to follow, even with the most powerful computers. And currently, the grid size, the box size, is about 100 kilometers for the workhorse models. And there are many phenomena in the atmosphere that happen on scales, on distances, smaller than 100 kilometers. Clouds, most obviously, right? And so if you have a grid box, which you describe by some temperature and humidity and wind and so on, you have to make some assumptions about what's going on with the clouds. You don't get to treat that explicitly in the model. And so there's a parameterization. You say, if the temperature is this much and the humidity is that much, there are so many fractional clouds at this altitude. Different people make different assumptions, and so they get different answers. And again, we're talking about 1% or a fraction of a percent differences that we're concerned with. And then there are these long-term modes in the climate system. This is data. This shows some measure of the temperature in the North Atlantic. And what you see is that it extends over, I don't know, more than 100 years. It's got a period of 70 years. This is called the Atlantic Multi-Decadal Oscillation I described for you before. The models will not reproduce this. They got to get the magnitude right, they got to get the phase right, the timing, and they got to get the period right. And the real climate system has got some instance of this, but the models may have a very different instance, and that messes up the comparison of the models with the data. So these are some of the problems that people have with the models. The chaos is not so much of a problem in the atmosphere. The atmosphere timescales are a week or two. Weather turns over on a week or two. The properties of the ocean change on much slower timescales. And there I'm willing to believe that there are chaotic things, but on the spatial scales we're interested in, I think it's multi-decades and not so much of a concern. The graph you referred to in the book, which was produced by Will Happer and William Van Gaarden, they showed that as the CO2 goes up, that the hole that the molecular absorption chops in the spectrum does not go up linearly. Roughly, it goes up logarithmically. And the difference between with the 2 times CO2 and isn't is very small. That's the 1% we're talking about, all right? It's there, it's calculable. What Will and Wim did, I think, is the best atomic physics calculation of that graph, that process. But you can find similar graphs for many decades, well, a few decades already. The logarithmic dependence is well known and is built into the radiation transfer models. You can find the logarithmic formula in the IPCC somewhere. So in that sense, no spectacularly new insights from Will's calculation, but a much more precise calculation with confidence. The logarithmic dependence, people know. With respect to whether the satellites have absorbed, we don't know, okay? The precision on the satellite, so you have to compare the infrared going out together with the solar coming in to measure the overall radiation balance of the Earth. And the number is less than a watt per square meter, but the precision of those two measurements is a couple watts per square meter, so you cannot determine it from the satellite measurements. The strongest evidence that's claimed for the planet warming up is the fact that the temperature of the oceans is going up. That's where the extra heat would go. It's going up at hundredths of a degree per decade at best, and as you might imagine, pretty difficult to measure. Nevertheless, we've got lots of floats out there now. There are 5,000 floats measuring the temperature. I'd feel a little more comfortable if we had a few more decades under our belt. Okay? Because again, you can get fooled by decadal scale changes. You can do a back-of-the-envelope calculation, and I do it for my class, and you can get the sensitivity right to within a factor of 3, roughly, okay? Just from Stefan Boltzmann law, t to the 4th. The real system has feedbacks, and again, for people who are not up on things, I'll just say a word about that. So, for example, if the additional CO2 made the atmosphere a little more effective in intercepting heat, and hence the temperature of the surface would rise a bit, then the snow and ice would be less, it would disappear, make the planet a little bit less reflective, and so induce additional heating. That's one that's called the ice albedo feedback. Another one, which is the dominant one, is that as the atmosphere gets warmer, it holds more water vapor and therefore becomes a little more effective in intercepting heat, because water vapor is the dominant greenhouse gas, natural. Exactly how strong these feedbacks are, and there are about 3 or 4 of them that we know about, is not something you get to put in the model. It emerges from the model. It's an emergent property. And as you saw, in about 40% of the models, things just go terribly bad. And so what the IPCC did was to really throw out those models and to try to estimate the individual feedbacks from other observations, including the energy balance of the different parts of the surface and so on. And when they then add them all the way back together again, they get a different answer than most of the models give. That to me is a little disturbing, because again, how could the individual feedbacks add up to something that's wrong in the model? And so the main paper is a paper, Sherwood et al. In 2020. You can find it on the web. It goes through feedback by feedback to try to estimate the sensitivities. So this is the biggest problem. Right? Cloud feedback, ice albedo feedback, water vapor feedback, lapse rate feedback, and so on.
So was the percentage of feedback and the percentage of the direct?
I'm sorry, say again?
Was the percentage
Oh, yeah. So it's easier to say it in terms of the sensitivity parameter. The sensitivity is boosted by a factor of 2.5 to 3 compared to the no feedback sensitivity. So if there were no feedbacks, there would not be an issue. We would see a degree rise and so on. So it is these unknown process feedbacks that are very difficult to determine, that are the uncertainty. These folks write for different audiences as well. I mean, when I read the basic research papers, pretty good, okay? Those guys who are all physical climate scientists, as opposed, when you get into ecology and impacts, it gets a lot softer. But I think as scientists writing research papers, pretty good, okay? Jim Hansen has evolved over the years. I think, the Jim Hansen of the last 20 years, Yeah, but the Jim Hansen of the last 20 years is very different than the Jim Hansen who did some really important work about surface temperatures in the 80s. All right? I think Gavin is capable of backtracking, as we've seen, but when those guys talk to the public, you get a very different sense. So Ray Pierre, when I wrote the first Wall Street Journal article, wrote in Slate, I think, what he thought was a scathing critique, and went so far as to suggest to NYU that they fire me. All right? He hasn't said anything about the book. All right? I mean, that's just, come on. All right? I mean, leave apart whatever technical criticisms he made of what I had written at the time, which, again, I don't think were really valid. All right? So, again, you get Gavin, you get any of these people in a room where you can have a serious scientific discussion, and I don't think they would disagree with anything I've said. But it would be great to get one of them up on stage and have that discussion.